Okay, please have a seat. We'll resume now. Okay, so I'm supposed to introduce the fourth invited speaker for this SIAM Geosciences 2015, and it's my pleasure to introduce Dr. Todd Ringler from Los Alamos National Laboratory. So Todd is the leader of the ocean science team with the Department of Energy's Accelerated Climate Model for Energy project. So his research interests are in geophysical fluid dynamics, computational physics, and also on the applications of global climate system models. Todd graduated obtained his PhD from Cornell in '96. Then he worked as a researcher in Colorado State University before he moves to the Los Alamos in 2008. So without further ado, I would like to invite Todd to the stage, and we're looking forward for your talk.
Thank you.
Thank you very much.
So thank you. So I want to talk today about a new global ocean climate model that we've been working on. So first, the acknowledgements. Thank the organizers for the opportunity to speak here. Thank all of you for turning out to listening. Now, we've been working on this for 10, 20 years, depending upon how you want to measure it. And over that period, pretty much all of my work has been supported by the Department of Energy, and in particular, the Biological and Environmental Research Office within the Office of Science at the Department of Energy. So gratefully acknowledge their support over the last 20 years. And also, we're going to talk about building a big computational physics model. Many of you have experience with those and know that there's a tremendous amount of work that goes into those. It's not a one-person job. It's a full team, and typically it's many teams with different expertise. And so there's three big parts here that I'm going to talk about. One is the numerical method. John Thuburn, Joe Klemp, Bill Skamrock were instrumental in helping to build the method I'm going to talk about. I'm going to talk about some grid generation. Max Günzberger is essentially the creator of this, with students of his, Lili Ju and Doug Jacobson. And we're going to pull these together into an ocean model. Michael Duda, Doug Jacobson, and Mark Peterson have been instrumental in putting that together. So, multi-scale global ocean climate model. So what is a global multi-scale ocean model? In this presentation, it's just a model that has different spatial scales in different parts of the ocean domain. And so here what we have is a simulation that we did a couple years ago where we put 7.5 kilometer resolution in the North Atlantic, and we have 40 kilometer resolution in the rest of the global ocean model. 6-year movie here, 1 frame per month. And what you'll see is that we have sort of eddy activity, mesoscale eddies throughout the global ocean, but through most of the ocean, say pick out the Kuroshio Current here, we have some Agulhas rings, kind of lethargic, rather weak. But where we've put our higher resolution, our 7.5 kilometer resolution, we have fairly active, almost eddy resolving resolution. So this is global multi-scale ocean model, resolve different scales in different parts of the domain. We are solving the same PD everywhere. So you could also call this a multi-resolution approach or possibly just a variable resolution approach. So why might we want such a model? The first off is in this grid, 75% of our degrees of freedom are here in the North Atlantic, and the entire rest of the global ocean, 25% of our degrees of freedom. So essentially, we've put 3/4 of our computational resources in the North Atlantic, in a region where, in this case, we wanted to study mesoscale eddy activity. So what I like to say is that the global model is for free. The grids I'm going to show you later on, we actually put more of our degrees of freedom in our region of interest, and you can easily get 90% of your degrees of freedom, say, in one area, and literally, the global model is for free. So the other reason we might want this model is simply to allocate our computational resources in our region of interest. So one more reason, and this is sort of the story that sells the method, I think. Another reason we might want this is to study sea level rise. It's sort of the canonical multi-scale problem for the global ocean. So what's going on here, we're going to have a mesh, and we're going to talk more about this mesh later on, but for the time being, we have 30-kilometer resolution in the global ocean. We come down to 5-kilometer in the Southern Ocean, where we can resolve mesoscale eddies. And then we come down even more to 1.5-kilometer resolution in the Weddell Sea. So if rapid sea level rise comes to pass, it will certainly emanate from regions around Antarctica. And how is that going to happen? That's going to happen because we have a shelf break here, which separates the Weddell Sea from the broader Southern Ocean. And we have relatively warm water, 2 Celsius water, which is very warm for the polar regions, sitting at depths of, say, 2 to 3 kilometers here in the Southern Ocean. This water comes up. Some of it can get over the shelf break into the Weddell Sea, and once it gets into the Weddell Sea, it can make its way under the Ronne-Filcher ice shelf, can melt the ice shelf. That ice shelf is providing a buttress, a support that's keeping the land ice on the land in Antarctica. And if we erode that buttressing, that ice from the land can flow down into the sea and lead to sea level rise. And then the water is going to melt here, but it's going to spread out through the whole global ocean. So we can't study this problem in isolation, in the sense that we can't just study this problem. We can't understand sea level rise by just going and looking in the Weddell Sea, because the water in the Weddell Sea came from the Southern Ocean. And the Southern Ocean has tied together waters from all of the world's oceans. So this is a global problem in terms of forming the water that lives in the Southern Ocean, but it's a very local problem in terms of how the ocean and the ice interact to lead to melt. So another motivation for this work is to resolve important processes that are intractable globally, okay? So we are probably several decades away from having a 1.5-kilometer mesh through the whole global ocean, but we can consider doing such a simulation like this right now, assuming that we had a model of the fidelity and computational efficiency to carry it out. Okay, so I think this begs the next question, which is, why are we just now getting around to this, right? Why don't we have such a model? Why don't all of the ocean model groups around the world use such a multi-scale model? The reality is that global ocean models have been around for about 40 years. And over the past 40 years, it's fair to say essentially all of the global climate models have used latitude-longitude grids, or possibly the variants thereof, where they take the pole and pull it into 2 poles or pull it into 3 poles and move those poles over the land so they're not numerically a problem. But I think it's fair to say there's not a tremendous amount of genetic diversity in the global ocean models that we use for climate change experiments and eventually feed into the integrated assessment reports. So why is this? I mean, these models are fairly entrenched, you could say. And so a competitor, a new model that becomes available, essentially has to pass a bunch of conditions. The first is that it has to be exactly conservative for mass and for traces for temperature. So this morning we heard about the hiatus and essentially variations in ocean heat content. First and foremost, if I want to understand changes in ocean heat content, my model has to conserve heat, okay? In the absence of sources and sinks, when I move temperature around, it has to be conserved. We're talking about tiny, tiny signals that persist for decades. Any small error in conservation can corrupt my solution. The second is we have to be acceptably conservative for some quadratic quantities, energy, potential entropy. We'll talk about this more. And finally, we have to be computationally efficient and accurate, about as computationally efficient and about as accurate. And so, there have been efforts over the past decade or two, and there's a couple efforts going on now. And what happens is that the efforts can't satisfy all of these. They can be accurate, but they're not computationally efficient, or they're computationally efficient, but they're not conservative. And so these are essentially ands. And if we're going to be successful in the global community, we have to satisfy all of these. So I think the short answer is the reason we haven't done it is because we essentially haven't had a computationally efficient mimetic method that supports these multi-scale meshes. So I've introduced the new concept here, new term here, this mimetic method, and one of the two threads that I want to talk about is how this mimetic method can actually help us crack these conditional ands. So, mimetic method, we had a whole session yesterday about mimetic method, so I'm guessing that many of you are familiar with this. Many of the talks have mimetic in the title, but just as a review. So mimetic is to imitate, and in this case to imitate the continuous system. And at that level, you could say all of computational physics is mimetic, because that's what we're trying to do, is we're trying to solve the continuous system. But in this case, it has a very particular meaning in the sense that we're trying to mimic sort of some conservation laws that exist in the continuous system. So even that is very broad, and in fact, like any good idea, it's been invented several times in many different areas of physics, and so it has different names. It's also called support operator theory. This is what it translated from the work that was done in the Soviet Union. I think in the broader CFD community, you'll see it referred to as a conservative finite difference method. In the ocean and atmosphere community, you often hear it referred to as the Arakawa method. The premise of mimetic method is that the exact representation of conservation laws trumps accuracy. Now, we want both. We want a solution that's accurate. We want a numerical algorithm that has high formal accuracy, but not at the cost of conservation. And it turns out that most mimetic methods are low order, including the one I'm going to talk about today. The reality is that if we place more value on these conservation laws than on accuracy, we typically end up with a fairly low order method. And I would argue that that's okay. So I said conservation laws. There are many conservation laws. Pick any PD you want, and you can come up with an infinite number of conservation laws. And here we're going to be talking primarily about the continuous rotating Boussinesq equations. And here's a list of the conservation laws that we found to be fairly important in terms of an accurate simulation of the global ocean and also the global atmosphere system. So as I alluded to before, first and foremost, if you're in the game of climate and climate change and you're integrating over centuries or millennia, absolute to round off error, local conservation of mass and tracers is a requirement. Conservation of total energy. We have two forms of energy. We have the kinetic, and since we're hydrostatic, the potential is sort of tied to the density field, which is largely tied to the temperature field. We want to conserve total energy, and we do that by satisfying some other laws. One is that kinetic energy is conserved under the process of advection. The second is that we have exchanges between kinetic and potential, and we want those to be exact, equal and opposite. And in the method that I'm going to discuss, we actually have problems. So when we're in the rotating system, we have the Coriolis force, and that Coriolis force is energetically neutral because it's always orthogonal to the fluid velocity, but and therefore it doesn't create or destroy energy. But depending upon how you cast your numerical method, that can be hard to satisfy. And then turning to rotation, or turning to the rotation part of the fluid, it's dominated by the rotational fluid or rotational motion, and conservation of potential vorticity is critical. And we get this by a Kelvin circulation theorem and combining that with mass. And so here's a whole list of conservation statements that we would like to support in our method. And it turns out that each of these statements essentially imposes some constraint on our numerical method. It might impose the formulation, the discrete formulation of the curl operator, or it might impose what actually our discrete form of kinetic energy is. And so each of these places a requirement, and it turns out that when we're done, essentially the numerical method we have is the numerical method that we have. There is no ability to make the stencil bigger to get more accuracy. We have a method, we satisfy these conservation laws, and then we use it and see if we're happy with it. Okay, so by way of introduction, and sort of by segue to the multi-scale part of this presentation, I would say the first mimetic method that really sort of changed how we do atmosphere modeling and then ocean modeling was the method put forward by Aurukun Lam in 1981. And he didn't call it a mimetic method. I'm not even sure that he knew what mimetic method was, but the premise there was he wanted to conserve energy, and in this case potential entropy, in a C-grid discretization. And so here we have a set of quads. We have an equation for mass here in the cell. The equation for the mass is just the divergence of our velocities, the u velocities to the left and the right, and the v velocities top and bottom. Okay, easy enough. We have an equation for the normal component of the velocity at the cell edges. And here I've written the normal component, I minus j minus 1, I plus 1. So it's the normal component of the velocity right here. We have the Coriolis force, and we have the horizontal pressure gradient force, which is just the difference between the mass here and here. But you see the first problem that shows up in the C-grid is that I need the meridional velocity, I need the v velocity at this u point, and I don't have it. And that's the crux of the C-grid method. I'm only keeping track of the normal components. If my fluid's rotating, I need a component of the velocity that I don't have access to. Now, while this is not a prognostic equation in the system, it turns out that this derived equation for potential vorticity is critically important in the quality of the numerical method that we're going to end up with. And I've written the equation for potential vorticity. You get it by taking the curl of this and combining it with the mass equation. But if we take the curl of this, what we find is the curl naturally lives here at the vertex of our mass cell. So potential vorticity lives on this cell, and it actually has a conservation law as well. This is a divergence, but you'll see each of these fields, each of these velocity fields, are velocity fields that I don't have. I need the u j I plus 1. That's here. I don't have that. I need the v velocity here. I don't have it. So all of the fields that control the evolution of the potential vorticity, I don't have. And this whole paper is about how do I reconstruct those fields in order to conserve potential vorticity, in order to make sure that this is a conservation statement in my discrete system. Now, it turns out on quadrilaterals, the naive reconstruction that you would think of doing is the right reconstruction, in the sense that I think I've written for the v velocity here, I simply go to my 4 nearest v velocities, average them, and that's the velocity I use there. Okay, there's a lot more to the Aurukun Lam than this simple reconstruction, but it serves as a segue to what we want to do. What we want to do is generalize these squares to this convex polygon. And if you look closely at this, you'll see that topologically they're kind of the same in the sense that I have a mass cell. I keep track of my normal components at my cell edges. If I want to take the curl of my velocity field, it naturally lives at the vertex. You also see that there is no sort of naive reconstruction of my normal components to build my Coriolis force or to use to transport my potential vorticity. It's not clear if you go to U1, let's see here, and I want to build my tangent velocity here, it is not at all clear how I combine, or even what I combine, to do that. So in the first of these papers, which is about 5 years now, we figured out how to do this reconstruction. And then the second, we figured out how to conserve potential vorticity and energy, essentially to build out the mimetic method. But there's a lot of lessons to be learned in just the geostrophic balance. So in the shallow water equations with a constant Coriolis parameter, there is a steady state solution. I'm going to use this shorthand delta for the divergence of the fluid. Like we had before, we have an equation for mass. These are all these equations are still linearized previously and here. So we have a mass cell. The time rate of change of the mass cell is simply some linearized value times the divergence of these velocities. We have an equation for the normal component of the velocity at the cell edges. Now, if we take the curl of this equation, what we get is an equation for the relative vorticity. So the curl of the grad goes to 0. That's one property that we have to build into our system. And this is often shorthand for U perp, right? K is the local vertical, K cross U is U perp. And U perp, when we take the curl of that, we end up with a divergence. So right, this conserves mass, and what we have here is a conservation statement as well. The time rate of change of the relative vorticity is simply due to the stretching and compressing of the Coriolis parameter by the fluid divergence. But I colored this blue because the divergence that enters into the relative vorticity equation is the divergence of these reconstructed fields. The vorticity feels the flow coming in and out of the vorticity cell. So now if we look for a steady state solution, we throw away all the time derivatives, what do we see? Well, we see that the fluid divergence has to be 0, so the div of my prognostic U has to be 0. But we also see that the blue divs have to be 0. The reconstructed velocity fields have to have a 0 divergence on the dual grid. And if we do that, then we get geostrophic balance. Fk cross U plus grad of phi is equal to 0, so we get a geostrophically balanced flow. So now we have actually a problem statement that we can use to reconstruct our velocity fields, and that is that both the div of U and the div of the reconstructed U perp have to be identically 0. Or I guess you would say that if this is 0, the reconstructed div of this has to be 0. So the statement, the mathematical statement that we used in that first paper was we reconstruct U perp such that the div on the vertices is equal to some convex interpolation of the div on the primal grid. We did that. It works. But there's a couple lessons to be learned here. The first is that other people have come into this problem and looked at it more from an order of accuracy reconstruction problem, right? I can use radial basis functions, I can use sort of a least squares, and I can come to this point and say, I want to reconstruct this vector. I got a ton of data. I can go out as far as I want. I can build a stencil. I can do a high order interpolation, and I can reconstruct that blue vector. That's fine. And I can do that everywhere. But what happens is you're very accurate, but you don't have this property. If you're reconstructing a velocity field that has 0 divergence very accurately, but your reconstructed field doesn't have a 0 divergence, what happens here? What happens is, okay, this is 0, but this isn't, which means there's a time tendency here, which in the nonlinear equations is going to feed back into here. which is then going to give you a divergence that's going to feed back into here. What you find is if you don't honor this property, you never get geostrophic balance. Your systems, these big anticyclones, just sort of wobble back and forth because there's always this imbalance between your reconstructed velocity field and your prognostic velocity field. And so this was a key, probably the key improvement that we found to make this method work. So the other kind of teachable point here is that if I look at this, so if I want to reconstruct this blue vector here in order to get the divergence here, I have to include in the stencil any velocity field that enters into the divergence of any of these cells. So the reconstruction of this blue vector here has to bring in the black prognostic from all three of these cells. And in fact, it can only bring in those velocity fields. It can't bring in any other velocity fields because those velocity fields don't affect the divergence of these three cells. Okay, so the second and final point I want to make about the mimetic method is you can build in a discrete Kelvin circulation theorem. And for the simulations I show later on, I think this is the key point to making the dynamics of our mesoscale eddy simulation robust. So Kelvin circulation theorem. So here I've written the momentum equation in nonlinear form. So I've in vector invariant form, and I've rewritten the u as u perp. So time rate of change of velocity, nonlinear Coriolis force, gradient of potential, and gradient of kinetic energy. And if I take the curl of that, what I find is that the relative vorticity here, doing something similar we did before, the relative vorticity here is 1 over the area of the vertex, the sum of these fluxes. So this is actually in a conservation statement. And it is the discrete analog to this continuous statement. And this is in conservative form. So what it means is that we obey the laws of the vorticity in the sense that we only change the relative vorticity due to stretching and compressing. And so we end up with a circulation that is conserved, and then I won't burden you with the details, but we can combine that with a mass and get a statement for potential vorticity that it is materially conserved following particles. And I think this is one of the few, possibly the only, multi-resolution method that has this Kelvin circulation theorem and has this identity for conservation of potential vorticity along particle trajectories. Okay, so just to sort of tie up this discussion about the mimetic methods, they've proved incredibly useful in a lot of different areas of fluid dynamics, but particularly geophysical fluids, and it's not always clear to why. Why have they been so successful? And I think there's two big reasons that lead to why. The first is energetics. I mean, I've talked here about the Coriolis force. Essentially, if you're not faithful here with how you reconstruct the Coriolis force, it's a bottomless source of energy. It will just continue to create or destroy energy without bounds. But sort of more subtly is that the fluid in these highly rotating flows is really tied up in available potential energy. And if I don't have a faithful exchange between available potential energy and kinetic energy, I can quickly corrupt the solution. If even a fraction of a percent, a spurious exchange from potential to kinetic energy will make the system blow up. And so that's one thing. Mimetic methods do that and do that well. The second thing is that these flows are highly rotating, and even a poor numerical method is going to try to conserve potential vorticity along particle trajectories. But if I have a spurious source of potential vorticity, it just gets added into the flow, and it gets carried along with the flow. The numerical method doesn't know whether that's a real vorticity or spuriously created. And so what you find is, if you have spurious sources of circulation, they're long-lived. They show up in the flow, and then they're just advected with the flow for long periods of time. And so what does this mean? These two things come together, I think, to lead to a conclusion that's a little soft, but nonetheless, I think is correct. Since we bound the flow, we've bound the energy, we've made sure we have a circulation statement, we've really constrained how the system can act. And essentially, we've constrained the system so that it cannot act too poorly, it can't blow up. And as a result, we need a minimal amount of dissipation. We need essentially the amount of dissipation that we should have in order to get the right energy and entropy cascades. And so what turns out, when we do the real-world simulations, since we're minimally damped, we end up with a simulation quality that's far beyond what we would expect from a typical order of accuracy analysis. Okay, so what demands does this place on the underlying mesh? We need a mesh that's conforming, and we need a mesh that's locally orthogonal. So we need a mesh that every cell center and every vertex has every edge is shared uniquely by two cell centers, and every vertex is shared by one edge, and it needs to be orthogonal. This needs to be orthogonal to that. The desired feature is we would like this to be composed of hexagons. And why do we want this to be composed of hexagons? And that's because I've written the weak form of the div here. I would like everything to be centered, right? This is a low-order method, and I'm only going to get second-order accuracy if everything is evenly spaced. So I would like U to be evenly spaced along this edge, and I would like phi to be evenly spaced within this cell, and I would like my vorticity to be evenly spaced within that triangle. And I'm only going to get that if I have perfect hexagons. So I want a variable resolution mesh, but I want perfect hexagons everywhere. So this mimetic method requires a Voronoi tessellation, or I would say a Voronoi tessellation is sufficient for this method. So a real quick introduction to these for those that might not have seen them before. So given some region S, within that region scatter around your grid points. We call them generators for reasons that will become obvious. So now plop yourself in this domain and find the generator, find the grid point that you're closest to. So, and do that for every point. So every point in this domain is going to be assigned to one of these generators, and then what happens is your mesh is all points that are closer to a generator than to any other generator. So this point, even though it's far flung, it is closer to this generator than to any other generator, and this is a Voronoi mesh. And it turns out that one of the properties of the Voronoi mesh is that the segments connecting cell centers are orthogonal to the edges. And it also turns out that many of you might be more familiar with Delaunay triangulations. The dual of the Voronoi tessellation is a Delaunay triangulation. If you know one, you know the other. Now, the method requires a Voronoi tessellation, but it's sort of not sufficient because this is a Voronoi tessellation, but it's not smooth. And what we do is we regularize that with this centroidal approach to make this mesh become something that we would use in our simulations. So a centroidal Voronoi tessellation is a way to build these smooth multi-scale meshes. Here's a picture that we saw before. Here are our generators. And what we do is we construct a density function. And you can build the density function from observational data. You can build the density function from analytic functions, anything you want it to be. And with that density function, we find the center of mass of each of these regions each of these Voronoi regions with respect to that density function. And we simply move our generator from there to there, and we redraw the Voronoi diagram. It's called the Lloyd's iteration, and we continue on until the mesh doesn't move anymore, until we've converged to a sufficient level of tolerance. And if we have a uniform density function, we say rho is equal to 0, so we want the mesh to be evenly spaced, these generators will evolve into these positions. Now, this is a mesh that we would certainly use for a low-order method. This is not, and so this process of making it a centroidal Voronoi tessellation has smoothed it. Now, we can do the exact same thing on the sphere, and in this case, we haven't made the density function uniform everywhere. We made the density function large within the blue region and small on the rest of the sphere. And so over the course of these iterations, what you see is the algorithm continues to move cells into our region of interest and away from a region that we're not so interested in. And it turns out that a priori, we can determine where our degrees of freedom are going to end up. So H here is the local grid spacing, and rho is this density function that we get to create. And D is the dimension, so here the D is 2. So given a density function at one point in space divided by the density function at another point in space, that tells me, when I raise it to the 1/4, what the ratio of my grid spacing between those two regions are going to be. Now, I won't go into detail here, but it turns out that I can get a mesh composed of perfect hexagons even if I have a variable density function. So you'll look at this, and you will certainly say, correctly, that these are not perfect hexagons. And in fact, they're not all hexagons. Like you see some pentagons here. You can certainly see some distorted cells out here. But if I hold this density function fixed and I continue to add more grid points, my mesh will get closer and closer to being composed with perfect hexagons. So this is a great way to guarantee mesh quality. I can always add degrees of freedom to get a mesh that is smoother and of higher quality. Okay, so let's build one of these meshes quickly. We saw this before. So we just start at a place. The density function itself is arbitrary, so we go to a high resolution. We set rho equal to 1. We're going to build a density function here. So now we go to the Southern Ocean, and we know that the density in the Southern Ocean, we just solve this for xj. It's the density function in around Antarctica by 1.5/6, which is our 2 resolutions raised to the 4. And we get that, so we know what density we want in this region. And then we go to the rest of the global ocean, we do the same thing. So now we know the characteristic densities that we want in these 3 different regions. We build a function that smoothly goes from one to another, and we're done. We seed our global mesh with a bunch of grid generators. We go through this Lloyd's iteration, and we end up with a lot of grid cells here and very few grid cells up there. Okay. So we have a method. We have a tessellation. Let's see what we can do with it. So I'm going to walk you through this double gyre system. So here what we have is a circular basin. Think of this as the North Atlantic. We're going to blow, these are westerly winds blowing this way, easterly winds blowing this way. We end up with a subpolar gyre, a subtropical gyre. We end up with western boundary currents that coalesce and lead to a jet that moves out here into the open. We get eddies everywhere, and we get this region of intense mixing here in the center. We're going to apply this problem with this multi-scale mesh, where we have 18 kilometers through most of the domain, and then we transition to 2 kilometers in a part of this region of intense mixing, and we're going to transition between the two. The Rossby radius of deformation here is about 30 kilometers. Through most of the domain, we're marginally resolving these eddies. And then through part of the domain, we're resolving them very well. And so here is a movie of the relative vorticity normalized by the Coriolis parameter. And you can see that we're going up to 1, so we're getting relative vortices on the scale of the Coriolis parameter, which means strong rotation. And this is not coming across quite as well as on the screen, but there's eddies all through here. They're relatively weak, which is why you can't see them on this image. But we have a strong eddy activity here in our region of interest. To kind of zoom in on this region, what you'll see is we have a western boundary current, and you'll see some eddies that live on the western boundary current. But you also see that as they come in through this mesh transition zone, they sharpen and sort of decrease in their spatial scale because they can. And then they come up here, separate. You'll see we have jets that exit. If you look at some of these, we have anticyclones that circle back and come back in. And we have down here a lot of anticyclones and cyclones that circle back and come back in. So we have very intense features coming into and out of our domain. And now if we blow up this one region here, you can actually see the mesh is relatively coarse here. And you can see it's relatively fine here by just looking at the boundary. And you can see these features roll up, exit and enter the high resolution region. But what you don't see are any artifacts of the mesh. And there's a single parameter that we have here for our turbulence closure, and that's just a hyper diffusion. So a mu del to the 4u. And all we do is scale this based on grid resolution raised to the 3/4, which gives us a factor of 10 for every doubling of resolution. So there's only one tunable parameter, and that's this mu0. And it's actually set in a completely different simulation and used here. But the important point is that our dissipation is the same, is using the same formula, whether it's in the mesh transition region or whether it's in the far away in the quasi-uniform simulation. The model doesn't know, the closure doesn't know whether it's in the mesh transition or not, in the sense that we do nothing special in the mesh transition zone. Now, clearly, things are going to happen in the mesh transition zone in the sense that if I have a very high frequency wave in my high resolution region, it's going to have to somehow be reflected or distorted if it wants to leave the domain. But what the mimetic method does is it makes sure that distortion conserves circulation, conserves energy, and it sort of bounds how that wave can act as it enters or exits the high resolution region. Okay, one quick real-world simulation. And so what we've done here is we did a global high-resolution simulation with 15 kilometers. And then we did a simulation that we just put 15 kilometers in the North Atlantic. And I think we used 75 kilometers in the rest of the global ocean. So the quasi-uniform 15 kilometers is here. The regionally refined 15 kilometers is here. And the difference between these two is the sense that this takes about 1/6 the computational cost is this. And what we're showing here is sea surface height variability, so RMS of sea surface height. And the only point I want to make is that they're identical. I mean, if you look very closely, you'll see some differences, but I would suspect that that's mostly just sampling error. And so this is just to make the point that we can reproduce, at least for this metric, all of the qualities of the global simulation by just putting the high resolution feature, by moving all of our computational resources into the North Atlantic. I think I'm out of time here. So that's one slide, and then we'll tie up. So this is just the computational performance for that quasi-uniform 15-kilometer resolution, simulated years per day against thousands of processors. Here's on two sort of typical clusters that we have at Los Alamos, scaling fairly linearly, and we could actually go quite a bit farther, but the cluster is only so big. And here this is on Mira. At Argonne, we've gone out actually to 70,000 processors, and our performance issues here are because we're only MPI. We haven't put in OpenMP threading yet, which we're doing right now. So this is a high-performance piece of software, and I think we can exploit essentially all of the DOE leadership class computing facilities that we're going to have access to. Okay, so the reason I said that we didn't have such a model, like the one I presented here, is that we have to pass this sort of gauntlet of conditional ands. Here are the list of conditional ands: conservation of mass, tracers, energy, computationally efficient, and accurate. So how have we done? So we have a pass. We're exactly conservative, the method that we've put forward here. In terms of conservation of quadratic quantities or conservation of potential vorticity, we're actually superior. We do better than, I would say, probably all of the existing IPCC class models. And then in terms of being computationally efficient and accurate, I think, we're in the hunt. We have a fighting chance. It turns out that on a per degree of freedom, we're 3 times slower than POP, so 3 times. But each of our degrees of freedom is more than 3 times as valuable as a degree of freedom in POP. So it's kind of a wash. You would certainly not choose this method based on its accuracy alone, but I think per flop, per degree of freedom, you're getting a competitive model with this new method. Okay, so where are we going? It turns out that the model I talked about here is the ocean component of this model for prediction across scales project. So I talked about the ocean. The folks at NCAR are building using the same numerical method, the same mimetic method, are building it for the atmosphere. We're building a land ice model and building a sea ice model that uses these same grid technologies. The ice components tend to use a different numerical method because there's not a high Reynolds number fluid. And so where are we going with MPAS Ocean? So the idea is that we're going to take this model, we're going to put it into the DOE Accelerated Climate Model for Energy, version 1. We're going to run a suite of climate change simulations going back to 1970, going forward to 2050. We're going to do global high resolution everywhere. We're essentially what we would call an eddy resolving configuration. We're also going to do a suite of these multi-scale simulations. Well, we expect the science on these real-world simulations will begin in 2016, and the idea is that ACME V1, this DOE climate model, will be released to the community in 2017. So I'll leave it there. Thank you.
Okay, so the floor is open for questions. Please use the microphones located in the center, or please go ahead.
Please, how does one take into account the temperature dependence of water viscosity in the model?
So our viscosity is not the molecular viscosity. The viscosity that we have in our system is not really the molecular viscosity of the fluid. It's more a turbulent viscosity due to a scale transfer. So we're many, many, many orders of magnitude away from the scale that molecular velocity would be important.
So one is a comment, and the other is a question. The comment is, you mentioned in the C grid that when they're doing the vorticity, you don't have U and V at that point where you do have the vorticity. But I found that to be slightly misleading because you don't need U and V, you need the derivatives. And the derivatives, if you do a center difference, is exactly at the right point. Although it's true that for the Coriolis force, then you don't have V in a U point, and that's a well-known problem of C grids. So just a comment there. And the other question is, you mentioned conservation of mass, and you also mentioned conservation of potential vorticity. Both of those depend on conserving or not mixing spuriously, incorrectly, your temperature and your salinity. And that's highly dependent on which vertical coordinate you're using. So I wonder, how does that, you didn't mention anything about the vertical coordinate.
Right.
So I was wondering, how do you conserve mass, especially in ocean and climate models? I think that's a big problem.
Right. No, that's a good point. So most all of these conservation properties that I've talked about here, we sort of derive for the shallow water system, so for the single layer system. So what we would want to conserve in the global ocean would be Hertel's potential vorticity, and that would require a very special vertical coordinate, say an isopycnal vertical coordinate. And if we were using that coordinate, which we're not, we could conserve, say, Hertel's potential vorticity, or do much better than present approaches for conserving that. So did I answer your so the vertical coordinate we're using now is sort of a z star. It happens to be an arbitrary Lagrange Eulerian vertical coordinate, so we can use isopycnal coordinates moving forward. But right now we're using what all of the traditional ocean climate models use, which is sort of a z level like vertical coordinate. Absolutely. So if you want to get water from top to bottom, you have to move it through however many vertical layers you have. Yeah.
Okay, any other question, please?
Could you tell me, does your CVT algorithm ensure orthogonality? Sorry.
So the CVT is just a special type of Voronoi tessellation. So a Voronoi tessellation guarantees orthogonality.
Yeah, but after you've smoothed, you were smoothing
Well,
afterwards.
so whenever you do your iterations, you move your generators around. Okay. Whenever you say I'm done, you draw the Voronoi tessellation for those generators. Okay, so you're still going to be an epsilon away. If I did another iteration, I would move my generator an epsilon point, but you don't do that. Whenever you're done and your generators are fixed, you draw the Voronoi tessellation, and that's the grid that you use in the algorithm. And since it's a Voronoi tessellation, it's locally orthogonal.
No.
Why do you consider mass conservation more important than momentum or energy conservation? You said mass conservation must be observed exactly. Yeah?
Yes.
The others as accurate as possible.
Yeah, that's true. You have to conserve mass exactly, because if you don't conserve mass exactly, you can't conserve any of your other tracer substances exactly. You can't conserve temperature, you can't conserve your biological trace constituents. So yes, that is more important than conservation of energy. And mostly, I mean, just anecdotally in our systems, that's what we observe. If you look at, you have to conserve mass. If you're looking at a signal of a sea level rise of a millimeter or a couple millimeters per year over centuries, you can't have an error in your mass equation that's even a fraction of that, or you don't know whether the signal that you're seeing is due to lack of conservation in your algorithm or due to physical processes leading to sea level rise.
Thank you.
Okay, so let's thank our speaker again. I think I believe you'll have the opportunity to meet up with him later in the day. Thank you again.